everyone. This is NagaLakshmi Devi, Assistant Professor, Department of Freshman Engineering, IARE, Hyderabad, Telangana. Now the topic is use of an analytic function, poles and residues. The definitions and singularity properties, definitions and problems. Now today starts with the geos of an analytic function. A geo of an analytic function f of z is a value of z such that f of z equal to 0. Particularly, a point A is called a zero of an analytic function f of z. If f of a equal to 0, if that f of a equal to 0, then it is called geos of an analytic function. For example, we are considering f of z equal to some example. This one, that is f of z equal to z plus 1 whole square by z square plus 1 whole square. In numerator is equal to 0. We are choosing that is the f of z. F of z equal to 0 means that one. Then the following now the z plus 1 equal to z plus 1 whole square equal to 0. Then find the roots. Here we get two roots. Why? Because here square is there. That's why we get two individual roots. That is z equal to minus 1 and z equal to minus 1 are zeros of an analytic function. If numerator is equal to 0, then it is equating to the roots. Then it is called a zeros of an analytic function. Okay, don't confuse here. The numerator is 0 means total is 0. No. Here, by using the zeros analytic function, numerator is equal to 0. That means we get two individual roots values. Then that is zeros of function. Maybe denominator 0, we get again two individual roots. Then that is called poles. Okay, next. This is zeros of the analytic function. Now, zeros of analytic function here, mth order. Zeros of, this is order, second order. Here it is second order. Now, we are discussing about the mth order. If an analytic function f of z can be expressed in the form f of z, if an analytic function f of z equal to z minus a to the power of m phi of z. This is the form. Where phi of z is analytic function and that phi of a is not equal to 0. Always that phi of a not equal to 0. This is phi of z. This phi of z we are substituting z equal to a, that is not equal to 0. Then that z equal to a is called the geos of mth order. Sometimes we are considering z equal to a, sometimes we are considering z equal to z naught also. Okay. That means in that condition z minus z naught to the power of m into phi of z, that phi of z naught is not equal to 0. Then z equal to z naught is called geos of an mth order of the function f of z. A simple geo is a geo of order 1. For example, the simple zero, the function is only one function is there, then the order is 1 only. Now, example, f of z equal to z minus 1 whole cube. For example, we are considering like that. Z minus 1 equal to z minus 1 whole cube equal to 0. Then z equal to 1. Only 1, 1, that the order is 3. Here power is 3. That's why the order is 3. In before example, the order is 2. In here, the order is 2. Here the order is 2. Here the order is 3 of f of z. Now here 1. That is, there is no function involved here. That means z equal to infinity is a simple zero of f of z. Then this function is called simple zero function. Now, function f of z equal to sin z. Now, the sin z is n pi. The sin z function is z equal to n pi. N equal to 0, sin 0 value. Next, n equal to 1, sin n pi. That means sin pi, sin 2 pi, sin 3 pi, sin 4 pi. All are zeros. Now, so that is also an simple zeros of the f of z. Now, next one. Definition of an analytic function. The permanent function definition is a point z equal to a is said to be a geo of an analytic function f of z. If f of z is a 0 at z equal to a. Now, if f of a equal to 0 and f dash of a is not equal to 0, sometimes by using f dash of a, then that is also not equal to 0, then z equal to a is called a simple zero of an f of z. Now, another function, the a 0 of the first order. If the 0 is the first order, then it is called a simple 0 function. Next, if f of a equal to f dash of a, that equal to f double dash of a up to so on, f n minus a 1 of a equal to 0, and fn of a is not equal to 0, then it is also called as a geo of an order n. For example, we can consider f of z equal to z square. The first derivative of z square is equal to 2z. 2z. Second derivative is 2. Third derivative is 0. That means f of 0 equal to f of 0 equal to 0. F dash of 0 equal to 0. F double dash of 0 equal to 0. All are f double dash of 0 equal to 2 only. Here there is no z function. Is 2, that is not equal to 0. Then z equal to 0 is a 0 of order 2. Here fn of a is not equal to 0. Here fn of n means 2. The order is 2. That's why n equal to, here n equal to double dash, that's why n equal to 2. The order is 2. That's why. For example, z square we are considering f of z. Now substituting z here, z value is 0, then it is 0. Now f dash of z, that is 2z. Again z value 0. F double dash of z equal to 2. Now there is no z value. That's why fn of a is not equal to 0 here. This concept is completed. Now f of a, f dash of a, fn minus 1 of a is all are zeros, and that means here these are zeros, but fn of a is not equal to 0, then that is called that nth of the order. Here also same, that nth of the order. But 0 of order n, we can write it as this one. In earlier one, it is directly, not in 0 of order. The direct order is 2. Here 0 of n function. That's why that order is 0 of order 2. Singular point of an analytic function. A point, singularity point or singular point. Singular point of an analytic function, a point at which an analytic function f of z is not analytic. That is, at which f dash of z fails to exist. For example, f of z is exist, that is analytic. But f dash of z is not exist. If that is not analytic, then it is called singular point, singularity of the function. For example, the f of x is analytic, f of z is analytic. Okay, now f dash of z is not analytic, then it is called at which f dash of z fails to exist is called singular point. Any analytic function is not exist, then it is called singular point. Not in any f of z is analytic and f dash of z, f double dash of z not exist, then it is called singular point of a analytic function. There are different types of singular points are there. First one is isolated and non-isolated singular points. A singular point z0 is called isolated singular point of analytic. Z0 is singular point, then it is called isolated singular point. Function f of z is, if they exist, a deleted epsilon, a neighborhood of z0 that contains no singularity. Here we don't have any singularity. Then that's a neighborhood of, there is no neighborhood of the neighborhood of point z0, then it is also called as non-isolated point, non-isolated singular point. That is third condition. Non-isolated singular point is the second condition. Isolated singular point. Now the next one. Thus, an isolated singular point is a singular point that stands completely by itself, embedded in a singular point. Then it is called a isolated singular point. Now here, regular points, isolated singular point. Now the regular points, that figure, next we can show it as a figure. The figure is there, where z1, z2, z3 are isolated singular points. Most singular points are isolated singular points. Here, all of the singular points are commonly we are using the isolated, then it is called isolated singular points. A non-isolated singular point is a singular point that every deleted epsilon, one element can be deleted, then it is called non-isolated singular points. Now if it is includes poles and immovable singularities, the essential singularities and branch of points. This isolated singularities points is added with the poles, immovable singularities and essential singularities. All are involved in isolated singularities. Next, this can be written as a point, singular point can be written as in by the definition, a point z equal to a is said to be singular point. The singularity of f of z is not analytic. That f of z is not analytic, then it is called a singular point. Now, types of singular point, first definition of the example. So, isolated singular point, a point z equal to a is said to be isolated singular point of f of z if f of z is not analytic, z equal to a. That is first one, singular point. Next, f of z is analytic at all points for some neighborhood of z equal to a. Some neighborhood is there, then it is called isolated, non-isolated singular point. That is example, f of z equal to z by z minus 1 into z minus 2. Then z equal to 1 comma 2 are isolated. This one, z equal to 1 and z equal to 2 are called isolated points. Now next, essential singular point. A singular point z equal to a is said to be an essential point of f of z if the Laurent series of f of z about z equal to a possesses the Laurent series. Means here we are considering e power x equal to x plus 1 plus x square by 2 factorial plus x cube by 3 factorial plus up to so on. That can be written as 1 by in terms of 1 by z. Then we can write is 1 plus 1 by z by 1 factorial plus 1 by z whole square into 2 factorial, like that. Then it is called, then it is Laurent series expansions. Now applying that one, the about z equal to a possesses the infinite number of terms. Now infinite number of terms in the principal part in terms of containing negative powers. In terms of negative powers also we are applying, then it is called essential singular point. For example, f of z equal to e power 1 by z. Then clearly z equal to 0. Now the singular point is e power f of z equal to e power 1 by z plus 1 by z by 1 factorial plus 1 by z whole square by 2 factorial plus up to so on. That equal to 1 plus 1 by z plus 1 by 2 factorial plus into 1 by z square plus 1 by 3 factorial into 1 by z cube plus up to so on. Here z equal to 0 is an essential singular point. Why? Because we are substituting z equal to 0, that is converted into in terms of infinity. 1 plus infinity, that is total infinity. Then it is called essential singular point in terms of containing negative powers. Next one is removable singular points. Isolated singular points are three types: isolated and essential and immovable. Now third one is immovable. A singular point z equal to a is said to be immovable singular point of f of z if the Laurent series of f of z about z equal to a does not contain the principal part. Immovable means does not contain the principal part. We are not considering the principal part, and remaining all are called as remaining all we are considering, then it is called immovable singular point. For example, f of z equal to sin z by z. Clearly here same, always the z equal to a, either at a equal to 0. Here z equal to a, that a equal to 0 we are considering. Z equal to 0 is a singular point. Then f of z equal to sin z by z equal to 1 by z is common. Sin z function, sin x equal to x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial, like that. Substituting that one. Now multiplied with 1 by z, we get z cancel. 1 minus z cube by z means z square by 3 factorial plus z power 4 by 5 factorial plus z power 6 by 7 factorial plus up to so on. Now minus z power 6 by 7 factorial plus up to so on. Here z equal to 0 is a immovable singular point. Here also same. Z equal to 0 we are applying. Then 1 minus 0 by something total 0. 1 minus 0 is equal to 1. Then it is called immovable singularities. We are eliminating these terms. Then it is called immovable singularities depending upon the given conditions. Now the Next definition and important one is pole. A point z equal to a is said to be a pole of f of z of order n if of order n, if we can find a positive integer such that limit z tends to a, z minus a to the power of n into f of z equal to f of z not equal to 0, then it is called poles. Now the first example problem, classify the nature of the singular point of f of z. They are asking singular point of the function f of z equal to tan z by z. Now f of z equal to tan z by using lines is tan z equal to z plus z cube by 3 plus z power 5 by 5 plus up to so on. Now multiplied with 1 by z, then 1 plus z square by 3 plus z power 4 by 5 plus up to so on. This is the law and series of the f of z. About z equal to 0 and there is no principal part. The principal part, there is no principal part. Only we get 1 only. Therefore, z equal to 0 is a immovable singular point. A immovable singular point. Immovable singular point means only one or something. Principal part we are removing. In singular point, 3 types are there. Which one satisfied this condition means here we are applying the singular point. Why? Because in singular point is 1 minus the principal part. The containing principal part we are eliminating. Does not containing principal part. Does not containing the principal part. That means we are removing this part. Only we get 1. 1 minus 0 plus 0 something. Only we get only 1. Principal part is removing. Then it is called immovable singular. Similarly, in this problem also we get like that. 1 plus this part is removing. Then it is does not containing principal part. Then it is called immovable singular point. Now then, also f of z equal to tan z by z. This can be written as sin z by cos z. We know the tan z value sin z by cos z. Now applying the poles. Here poles is nothing but denominator is equal to 0. Z into cos z equals 0. Here that is the function. They are applying that also. That one. Okay. Now z cos z equal to 0. Now z equal to 0, comma n z equal to n pi. Here two functions we are occurring. This first is z equal to 0. Z equal to 0. Next cos z equal to 0 means n pi. Cos z equal to 0 is nothing but cos z equal to n pi. Okay, that n equal to compulsory here n equal to compulsory 0 plus or minus 1 only. We get finally 0 plus or minus 1. For example, cos n equal to 1. N equal to 0, 1, 2, 3 up to so on. Cos 0 value 1. Cos 1 value n pi cos pi minus 1 whole power n minus 1. 0 now substituting 0 here we get 1. N equal to 1 we get minus 1. N equal to 2, n equal to 2 pi, that is 1. Like that, continuing this process up to so on, then n equal to 0 plus or minus 1. Now the condition is satisfied. N equal to 0 comma plus or minus 1. Here 0 comma plus or minus 1. 0 this one and plus or minus 0. Plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. That's why we are considering plus or minus 1 simply. Now z equal to 0 comma n pi. Are simple poles. The pole of order 1. Here order is 1. Here order is 1. Oh sorry. Now here. Now order is 1. That's why the poles of these poles are simple and it is order is 1. Order is 1 is called simple poles. And 0 is also there. That's why simple zeros. Consider the function f of z equal to, another problem is this one. Consider the function f of z equal to sin z by z power 4. Find the poles and its order. F of z equal to sin z by z power 4. 1 by z power 4 common. Now remaining is z minus z cube by 3 factor sin z function. Z power 4 by 5 factorial. Now multiply the 1 by z power 4 in this function. Now z by z power 4, that means 1 by z cube minus 1 by 6z plus z by 120 minus up to so on. Now substituting here z equal to 0, then we get the 0. Now here this is 0, here also 0. the total function is 0, then the order is 0. Then the order is 3. Here the order is 3. That's why order is 3. Then it is 0. Now next one is definition of residues. The residue of a function f of z at a singular point z equal to a is the coefficient of b1 of 1 by z minus a in the Lorentz series of f of z. Now about the point z equal to a is a definition of the residues. Now the evaluation of residue like this. Now the definition of residue is the residue of a function f of z at a singular point z equal to a. That singular point means either removable singularity, poles, or some essential singularity, whatever it may be. Z equal to a is the quotient b1 of 1 by z minus a in the Lorentz series expansion. Compulsory we are applying the Lorentz series expansion of f of z about the point z equal to a. Now the evaluation of residues. How to solve the residues in the given functions. Suppose z equal to a is a pole of order 1. Just they are considering, for example, z equal to a function f of z equal to 1 by z minus 1. Here order is 1 only. That is the example they are given. The residue of f of z equal to z equal to a, limit z tends to a into z minus a into f of z. If suppose this is the formula, and another one, suppose z equal to a is a poles of order n. That means f of z equal to 1 by z minus 1 to the power of n or 10 or something. Here order is 10. Okay. Now then the formula is then the residues of f of z equal to f of z as z tends to a, limit z tends to a 1 by n minus 1 factorial into d power n minus 1 by dz power n minus 1 into z minus a whole power n into f of z. This function is here, for example, we are considering simply it is 10. Okay. That means here limit is z tends to this is 1. Now the function is 1. That means z minus a equal to 0, z equal to 1. That's why I am considering limit z equal to 1. By 1 by n minus 1 factorial. Here n equal to 10. Here n equal to 10 means 10 minus 1. That is 9 factorial into d power n minus 1. That is 9. By d power z power n minus 9. N minus 1 is 9 into z minus a. Z minus 1 whole power 10 into f of z. F of z 1 by z minus 1 whole power 10. Both are cancelled. We get this one. Maybe if here it is any z cube is there. Now here d power 9 means z cube. 3z square first derivative. Next 3z square. Z cube is there. For example, here z cube is there. The first time derivative is 3z square. Second time derivative is 6z. Third time derivative is 6. Fourth time derivative is 0. The total value may be 0. For example, here 11 is there. For example, 11 is there. Then we get the value. 9 times derivative, we get the value. Then again we substitute the z equal to limit z tends to 1. Then after. Now that is the poles of order n of residue. Next, suppose z equal to a is a pole of order 1 and f of z equal to p of z by q of z. Now p of z by q of z is defined. Then the residue of f of z equal to a, p of a by q dash of a. P of a by q of a is another function is there. This is defined by using L'Hospital rule. We are solving like this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.